Hello, I'm Nick Rychek. In today's video, we are going to be finding the elastic modulus, how you find the yield point, how to read out the yield strength, how to find tensile strength, how to find the ductility, percent elongation, and percent reduction area, how you find the resilience, and how you find the toughness of certain materials. Let's start with one of the most important material properties, the elastic or Young's modulus. This tells us how stiff a material is, basically how resistant it is to being stretched or compressed when you apply force. The higher the modulus, the stiffer the material. To determine Young's modulus in an experiment, we perform a tensile test. First, we take a specimen of a material with a precisely measured cross-sectional area and an accurate initial length. Then we mount it in a testing machine and apply a gradual increasing load. At each load increment, we record two things: the force being applied and the amount the specimen has elongated. From the recorded data, we calculate stress by dividing the force by the original cross-sectional area. We also calculate strain by dividing the change in length by the original length of the specimen. When we plot stress on the vertical axis against strain on the horizontal axis, the first part of the curve is a straight line. This is the elastic region, where the material behaves like a spring and will return to its original shape when the load is removed. The slope of the straight line portion of the stress strain curve is the Young's modulus. A steeper slope means a stiffer material. A shallower slope means a more flexible one. So by preparing a sample carefully, applying a controlled load, measuring elongation at each step, computing stress and strain, and then finding the slope of the initial linear region, we can directly determine the elastic modulus of that material. As you can see on the steel and aluminum stress strain curves, the constant slope of this graph is where Young's modulus begins. On the copper stress strain curve, you can also see the same thing at 100 megapascals, where Young's modulus also begins.
Yeah. Thank you for the valuable information, Nick.
Yeah, no problem.
I'm Ozan, and we're going to be explaining yield point. Yield point is where a material stops behaving elastically. Yield strength is the amount of stress that corresponds to that point. On a stress strain curve, when you test the sample, intention and put stress on the y-axis versus strain on the x-axis. When the elastic region on the graph starts to deviate, this is the beginning of the yield point. So as you can see on our graphs for steel, it starts to deviate around 150 megapascals, given our yield strength. And also, as you can see on the aluminum graph, it starts to deviate around 200 megapascals. And looking at the copper graph, it starts to deviate around 100 to 150-ish, given our yield strength.
Thank you, Ozan. Hi, my name is Tristan Allen. I'm talking about tensile strength. Tensile strength means maximum stress in a material that can stand in tension before it starts necking and ultimately breaks. To find tensile strength, you must measure the maximum load a material can withstand before failure in a pull tester. Then compute the tensile strength with the force over the original cross-sectional area.
Thanks, man. Cool. When you need to find the ductility measures of a tensile test, one being percent elongation, where you must find how much the gauge length stretched overall, including necking. The other being percent reduction of area, where you need to know how much the minimum cross-section shrank at the neck.
Thank you, Nick. Guess who's back? Ozan with another wonderful presentation. So, resilience. Resilience is the energy a material can absorb per unit volume within the elastic region. On a graph, this is the area on the stress strain curve up to the yield point. As you can see on these graphs that are drawn by our wonderful artist Nick, right around for the first material steel, around 200, the red shaded area is our resilience. To find that red shaded area, by taking the integral of the stress from 0 to the yield point. As you can see on our other graphs, for aluminum and copper, both red shaded areas are around the yield point coming down to the tensile strength.
Thank you, Ozan. So now let's talk about toughness. The toughness of a material is the energy a material absorbs per unit volume up to the fracture. On a graph, this is the entire area under the stress strain curve from 0 until the fracture. You find this by taking the integral of the stress from 0 to the point of fracture. As you can see in our graphs, for steel and for aluminum, the entire red shaded area is what describes toughness.
So,
Put that.
one. So to wrap up, here's what we covered. The slope of the straight part of a stress strain curve gives us Young's modulus, which tells us how stiff a material is. The point where the curve stops being straight is the yield point, and the stress at that point is the yield strength. The highest point on the curve is the tensile or ultimate strength, the maximum stress the material can handle before it starts to fail. Ductility is how much the material can stretch or thin before it breaks, measured by percent elongation or percent reduction in the area. Resilience is the energy a material can absorb per unit volume before permanent deformation, which is the area under the curve up to the yield point. And toughness is the total energy a material can absorb per unit volume up to fracture. These are the key properties you get from a tensile test. Thank you for watching. I'm Nick Rajak.